Hey, this is Kenneth, and today I'm going to work on trying to fix a GM300. Well, not actually a GM300. I mean, first of all, the keen will spot that this looks like a GM300, but actually isn't. This is a M120. The GM300, which looks like this, you'll note has a 2-digit 7-segment display, 5 buttons, a volume knob, and was a really popular commercial VHF, UHF land mobile radio back in the 90s. Unfortunately, to narrowband these was kind of an involved process, so that wasn't very popular, and by then Motorola had newer, more sophisticated radios with better signaling features, and so a whole bunch of these got just decommissioned about a decade ago. As part of that, I kind of ended up with a whole pile of them with various neurotic problems, and I'm finally getting around to poking at a few of them. So this one is an M120, which is essentially the same as a GM300, except instead of it having two 7-segment displays and 16 channels, it only has 2 channels and a single button to toggle between them. I love this because I use these for mainly APRS, where I only need to have 2 channels anyways. You've got the standard 144.39 megahertz channel, and then for special events or something you'll use the 144.99, and so the M120 is exactly what I want for it. They're typically about a 25 or 40 watt radio. They have this incredibly nice, on the back here, 16 pin connector that you can order these connector shells and build your own cables with them. And this has everything you need. It's got carrier squelch, it's got push to talk, mic in, flat audio in, receive audio, a couple I/O pins that, depending on exactly what internals you have, you can actually reprogram them to like output certain things like PL decode, or there's several different things that you can program it for. So anyways, so this radio is DEF. So what we've got is on the mini UHF connector back here, which is really kind of an awful connector, I've got a BNC adapter just parked on there. We've got the 12 volt bullet connector and a 12 volt power supply here. We've got a cable going up to my service monitor. So this is a HP 8935 series. These were real popular service monitors to get on the secondhand market when CDMA kind of went out, because they do CDMA, but they're perfectly usable for VHF, HF, UHF, land mobile, FM stuff, right? And so we'll be using that. Then we've got a monitor for that computer, which is booting DOS, because while Motorola can make radios that last 3 decades, their radio service software, RSS, still requires DOS and did not age quite as gracefully. So to talk to this, we'll be running MS-DOS on that system. It has a real serial port. Then on eBay, I got one of these. This is the Motorola RIB radio interface box. And so on one side, it's just got a serial cable. And you can't just use like a standard you can't use like a USB adapter, because what Motorola does is they're bit banging on the serial port to to bit bang their one-wire protocol that they talk to these radios over the microphone connector. So you really do need a real serial port on this. Thankfully, the GM300 RSS is new enough that it doesn't require like an actual 386 as far as like clock frequency. It runs perfectly fine on this. This Optiplex FX160 is running like some random Atom x86. So I'm booting DOS on there. It runs it perfectly happy just because it has a real physical serial port on it. The radio interface box comes to a DB25, and the reason they do that is they actually have several different voltage levels and like shifters and stuff here, and then your adapter cable that goes from the RIB 25 pin to whatever your radio's connector is, be it a 8P8C for the mobile rigs, or like a little clip-on HT microphones and stuff. It also has a couple loops in here to configure this electrical interface to correctly talk to whatever you're talking to, right? And so I didn't want to buy an actual Motorola rib, so I got one on eBay and then built my own adapter dongle for it for this. So, getting to this. So what do we know? So it's an M120, which is essentially a GM300, but it's only 2 channels. Looking at the part number here on the back of the bottom of the heatsink on the back, the model starts with an M43, and I just kind of use the mnemonic that when you talk about a radio, you're going to talk about a high power VHF or a low power UHF, and so the first number is the power level and the second number is the band. So 4 means that this is a high power, so it's like 25 to 40 watt, and then the 3 means that it's a VHF. If it was a model 4.4, it would be a high power UHF. If it was a model 3.3, it would be a low power VHF. So in this case, we have a high power VHF M120, which in my handwriting from about 3 years ago, apparently I say high power V and that it's deaf. So let's get into this and see how it goes. So turning on the service monitor, plugging in the rib, plugging in the serial port, plugging in service monitor, plug in 12 volt power, turning on my power supply. Okay, so first encouraging news, it turns on, right? So fantastic. The monitor light lights up because we don't have the microphone plugged in and on hook, which is fine. You can see you can switch between the 2 channels, so that's very exciting. So the buttons seem to work. The beeping we're hearing is coming from the internal speaker, and the internal speaker is making noise because of this, like a dongle here. It has 2 pins for the external speaker if you wanted the speaker somewhere else, and then it has one of the pins for the internal speaker up here as well. And so the fact that we have pins 15 and 16 looped back together here is why this is making noise. If we were to unplug this, this now no longer makes any sound. It's expecting you to have an external microphone. A common trick that people will use if they don't happen to have one of these adapter dongles is, since it's 15 and 16 and these pins are on a 0.1 inch spacing, if you just take a standard motherboard jumper and put it in there, you can make the front panel make sound. I typically have a few of these for testing, and then my actual terminal node controller modem interface cables, I don't have this, because I figure that wherever I'm installing this thing, whoever is standing nearby probably doesn't want to listen to APRS squawks. So anyway, so there we go. So we got that, and we've got up here DOS and the service monitor. Let's see how I want to frame this up. Maybe something like that. So let's see what we can do to talk to this radio. So in DOS, I have a folder where I have, on the internet, found a pirate copy of the GM300 RSS. So we go into that, press any key. We want to get save, read radio, and then this is it downloading the code plug, which is essentially, the code plug is essentially this binary blob that has all of the calibration data, the channel selections, because commercial radios don't have just a dial in the frequency you want. They really lock you down to only a specific set of frequencies, which for APRS is exactly what I want. But so having now downloaded the code plug, I can navigate over to change view code plug data. And RSS is actually kind of weird in that all the navigation is by your function numbers. I don't know, kind of amusing. Alright, so we can look at our modes. And yeah, it looks like I have in fact been in here before, because we can see that for the first mode, which is channel 1, receive frequency 144.39, transmit frequency 144.39, carrier squelch, timeout timer 30 seconds. So yeah, this is a pretty standard APRS configuration for me. And so now, ideally, if we were to go to the RF generator on the service monitor and go to 144.39 megahertz, so I'm generating an FM signal at 144.39. Let's see if, does it make sense to zoom in on this maybe? We're going for low production value today. So 144.39 megahertz. I'm going to have it go out through the high power RF out. I'm going to modulate it as an FM signal with 3 kilohertz deviation with a 1 kilohertz audio generator, which is fantastic. An amplitude, I'll start at like 1 microvolt, which on a healthy radio, 1 microvolt is a ton. This would immediately, like a typical GM300 open squelch at about 0.2 microvolts, and you're full quieting up at like about 0.7, 0.8. So we've got 1 microvolt, we've got no squelch indication, we've got nothing. 2 microvolts, nothing. 10 microvolts, nothing. 50 microvolts, nothing. So yeah, this thing's just completely deaf. So let's go back to 1. And so, yeah, on the receive side, deaf as a doornail. So we can check the transmitter on it, which, I mean, if presumably, it seems like I've checked this thing out at some point, so if the transmitter was dead, I probably would have noted it. But anyway, so if we go to so I went back to the main menu here in RSS, and we're now going into the service menu. So the service menu is, I'm not just changing channels, I'm actually doing some sort of alignment actions here. And kind of the 2 categories of actions you get is alignment, where you're just doing fine-tune tweaking, or board replacements, where you've swapped out a whole board on the radio, and you're going to go through the whole, let's dial this in like it was new for the factory. We just want to test if the transmitter works, so we're going to go to alignment, and then we're going to go to transmit power adjust. And so what this does is it puts you in this mode where eventually, alright, so this 0 to 126 bar here is the bias adjustment. That's a digital analog converter inside the radio for how powerfully it biases the third to last stage in the amplifier, which then ultimately controls what our final output is. And so the GM300, or the M120 in this case, has, this is one global value for setting the total power across the whole band of operation, which is 146 up to, I don't know, 170, 165. So it's currently set for 90. And so, unfortunately, they don't tell you what the frequency is until you key it up, but it's burned into my brain. So I believe it's, 159.52? I say it's burned in my brain, and then I immediately blank on it because I've been switching back and forth between VHF and UHF. I was close. 159.125 megahertz. Tell me about the RF in. Let's lock the attenuator at 35 dB, and the input attenuation on the service monitor has an automatic where it auto scales or a hold. I like hold because, just like a digital multimeter, when it's not in auto scale mode, it gives you a reading faster, which helps me see some issues. And so in this mode, I can hit F6, that will, over the radio interface box, key up the radio, right? And so if we go look down at the radio here, now we're to press F6, there's some talking, and then the radio keys up, which I guess there really isn't much display of that on the M120. But anyway, so given that, we key it up. We see we're getting 26 watts out. We have a frequency error of we're about 350 hertz low, which for a cold, M120, that's pretty good. They tend to drift quite a bit, and as long as it eventually, once it warms up, drops. Oh, geez, look at that. Well, I say it eventually warms up and dials into about, plus or minus 200. I'm pretty happy with it, although something's going wacky with it right now. Okay, yeah, there we go. So 25 watts, like 17 hertz off. So, and then you can, while it's keyed up even, I can press the down arrow and that adjusts this bias number, which translates from 86 is now 21.8, 85 is 20.9, 84 is 20 even, but I'm perfectly happy with about 25. So 90 bias gives 25 there. Fantastic, right? So transmitter seems to be pretty great. If the frequency was off a little bit more, then 7 hertz. That's dumb luck. There is another alignment mode for reference oscillator warp, which adjusts a tiny capacitor digitally on the reference oscillator, but we'll just skip that. So anyway, so now we know that the first channel on this thing is set up for 144.39, and we know that this thing is completely deaf. So at this point, I think we need to open this thing. The nice thing about the Motorola's is that you actually pretty much just need an M10, or not an M10, a T10 and a T15 Torx, which gets you through pretty much all of the screws. On some of their repeater systems, like the R1225, they actually have the audacity. They use a T20 for a couple of the real heavy-duty mounting screws, but like practically every screw in the GM300 is T10 or T15. So anyways, head unit comes off. There's actually very little. Oh, last person was nice enough to stick some. Ooh, yeah, there we go. Velcro. The head unit is actually almost completely unintelligent, and so literally all it has is these two connectors, which go to, like, this runs the 7-segment displays, this runs the speaker and the volume pot and the microphone jack. That's it. There's no intelligence here. Interface pins here, and you have to pull that head off because there's like a I don't know, like a lip there, and so the front head locks these top and bottom panels in place. So on the side here, come on, 2 screws on the left side, 2 screws on the right side, and a nice thing about the case of these is that they're rotationally symmetric. So the top lid and the bottom lid are exactly the same, and then the 2 RF shields inside of it for the top and the bottom are also the same. And so unless you've got like a bunch of labels on these, or in this case Velcro feet, you don't really need to worry about keeping them straight. So I'm giving you that compelling YouTube content of me screwing around. There's 3, and there's 4. Alright. So they're two hermaphroditic shells that kind of nest into each other, so you just kind of gotta apply upward and downward force and they kind of shimmy apart. Two plastic shells, we can set those aside. And in the radio itself, we have the top and bottom shields. So I like to take a relatively large purpose-built prying device, because you never want to use tools for not what they're designed for. And then you just kind of apply some upward pressure. And then I use that to kind of just lever the whole thing out. Nice press fit. So this is the RF shield, and then it's just got insulator there. And we're looking at, this is the RF deck, right? And so the front head, it was literally just display and controls. This is the RF section, and so this is what has the receive circuitry and the transmit circuitry and the variable frequency oscillators, like all the synthesizers inside that shield there. And then it has this 14-pin connector here, which actually goes through the board, or like through the whole chassis, over to the other side, where we have the microcontroller and like the audio stage, right? And so there's the feed through. Here's your microcontroller section, so this is what, you know, makes it intelligent. Audio section, and then this is your control cable out to the power amplifier and power coming back in to the rest of this board. And so these 6 pins is what switches on and off the power supply and transmit receive. And then the 2 pieces of coax coming out, the transmit synthesizer in here, an exciter, goes out through this coax to the power amplifier and amplifies out. And then on the receive pathway, it goes from there through the transmit receive diode switches in the PA section, through this piece of coax, lands here, and then goes along. This is the whole receiver front end right here, right? And so this piece of coax there, and then you've got your various capacitors, inductors, first preamp, and etc., etc., all the way to the first mixer there, which this is the part that converts whatever frequency you're receiving at down to a single 45.1 megahertz. And then that goes through this set of filters here, which actually includes 2 crystal filters, that are quartz crystal filters. And so this part only ever has to receive at 45.1 megahertz because we've mixed it down to that. And then this chip here that has the RF board calibration numbers on it, if you're doing like a full board replacement, so don't peel that sticker off, this is what demodulates it to audio and feeds it through this header down to the other side. So great. Opening up this cage here. Oh yeah, this is definitely premium technique as far as getting this stuff out of here. So here we've got the reference oscillator section and the phase lock loop synthesizer. So like this is your reference 14.4 megahertz crystal that this whole radio's concept of frequency is based off of. And then these are the 2 variable frequency oscillators for receive and transmit that let you have the radio tune around. So anyway, so we're mainly interested in the receiver section now. So first thing I'm going to look at is, if we're lucky, this blue potentiometer right here is the receive squelch. So we're going to make sure that we've still got our internal speaker adapter plugged in. I'm going to reattach the head so that we can see what's going on here and hear it. Apply power. RF generator, amplitude 1 microvolt into the RF, nothing, right? And so if we were lucky, it could be entirely deaf just because the squelch is turned up. So this blue potentiometer here is the squelch. We can turn it. We can turn it down, and the squelch opened. Fantastic. So, what happens if we turn? Okay, so that wasn't it. That would be a disappointing video, I think. So like I turned up to 10 microvolts, still nothing. So turns out you can turn this all the way down and you get, you know, noise. That's not an actual testament to it having received anything. That's just you forcing squelch open on absolute zero. So we're gonna have to start putting some more work into this. So I've got a copy of the service manual open on my laptop. I'm pulling up the schematic for the VHF RF board. VHF RF board. Alright, receive pathway. RX. The first diode is clamping protection, and then there should be a transistor around a 15-volt resistor. So I'm looking on this pathway here. So let's take the receiver pathway out of it. And so from here we've got about 9 stages of LC filtering, which we can see up to about there. That SOT23 there is a clamping diode, and so that's just one diode up and one diode down, so that if the voltage here, right here, goes above 0.7 volts in either direction, you know, it conducts, and that just kind of, that protects all of the rest of this from some sort of gratuitous overload. And then I'm willing to bet that that right there, yes, that's our first preamp. So that's just a little M50X01 RF amplifier with a 150 or 15 ohm resistor there. Unfortunately, Motorola boards like this don't tend to have silkscreen. And so while the schematics have reference designators that I'm looking at, you have to then match it up with, they have another page in the service manual that is like device placement. So you get really good at like just like looking for resistor values. So what we've got here is we've got the other output from my service monitor, which we're going to switch to that. At the end of it, I just have a piece of coax with ground and center conductor separated out separately, so that I can now sit here and probe around with an RF signal, right? And so I can sit here and probe that, nothing happened, right? And so I was feeding 2 microvolts in at the clamping diode, and so that assures me that, okay, it was possible there was a problem between the antenna connector through this front end. So like if the TR switch here was busted, this should have worked right there. It did not, right? And so that indicates to me that the problem is farther upstream. So now so the next thing is, it's possible that the issue is the preamplifier, right? If that amplifier was completely smoked, we would be having a bad time. And so I know that this preamplifier typically gives you about 16 dB of gain, and so where I would be probing around with 2 microvolts right now, which is about minus 100 dBm, I'm going to turn that up to about minus 84 dBm, and so we're essentially simulating that amplifier by turning the power up. And I'm making absolutely sure that I'm probing the right place. Hold the shield down. Nothing. Okay, and so problem is after amplifier. Okay, looking at the schematic. There should be a 100 ohm resistor on the mixing. Yeah, so the mixer here consists of this transformer, and then diode ring, and the SOIC 8 package there. And so I'm going to again inject it right into the mixer. Nothing. Okay. Right, and so whatever the problem is, it's after the mixer. So let's go back up to, yeah, and this is real exciting here. I'm describing reading a service manual to you. So we're going back to the receive pathway conceptual overview. Receiver back end, receiver front end. Alright, the first mixer is a passive double balanced type consisting of T1, T2, and U1. This mixer provides all the necessary rejection and high side injection at 13 dBm. Delivered to the first mixer from the synthesizer. The mixer output is connected to a diplexer network that matches itself at 45.1 megahertz and terminates itself into a 50 ohm resistor. Okay, so now I'm going to go up to my frequency generation. Alright, so our signal generator, which was at 144, we're now going to go to 45.1 megahertz. Beep, beep, beep. And now, conceivably, if we were to start, we've now kind of simulated that mixing conversion. Q51 amplifies the IF signal by approximately 17 dB, and the output of Q51 is filtered by a 4-pole crystal filter, which is that and that, which implies that right before those crystals, we've got like a Q51 somewhere. That would be a real nice place for us to inject yeah, Q51. It's a FET. Right next to what? Inductor can and like a 3.9 kilo ohm resistor with a grounded gate. Yeah, so that's the grounded gate. So I'm willing to bet that the input we're interested in is that one right there. Nothing. Alright, so just as a sanity check, I'm going to like completely open the squelch and then feed the modulated signal in to see if the issue is like the squelch. Like if like the squelch isn't operating, but like the actual you know, the output, like if the actual, what am I trying to say? If the receiver was working but the squelch circuitry logic wasn't, then we would hear a tone there and we didn't. Okay. Crystal lattice, crystal lattice. Out of crystal lattice. Got another amplifier right there. Okay, I didn't like that. I managed to wedge my reduce input, switch, measure, reset. Measure, reset. Where's the measure reset button? I know, I'm so sorry. What did I do? Oh, come on. Reference set, centennializer scope, measure reset. Measure reset. Okay, alright. Okay, so we didn't want to probe there. Pin 19 on the receiver system. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19. Pin 19 on the receiver system? That sounds right. Man, this thing is completely smoked. Right? I mean, 14, 15, 16, 17, 18, 19. Absolutely nothing. Okay, so I've kind of tapped in a few places along the way, injected signal, and we haven't gotten any indication of life, which makes me question, is the RF, is the receive side local oscillator even alive? Okay, so let's start looking at our receive synthesizers. Receive VCO frequency. Alright, so the inside of this cage we have this phase lock loop here, which this is running one variable one voltage controlled oscillator for the transmit side and one voltage controlled oscillator for the receive side. The reason they're two separate ones is probably because they're totally separate. They're probably really different frequencies for the receive IF chain versus the output IF chain. So let's start doing some sanity checks that our receive oscillator is, you know, trying to oscillate. So multimeter. And what am I probing for? Receive VCO. Alright, so there's going to conceivably be 4 diodes. Yeah, so there's 4 diodes here. That is our varactors for adjusting the frequency. There's a decoupling cap. There's an inductor to ground. Sure. Yeah. A capacitor. .5 volts. 56 ohm resistor. Okay, so does that mean that this here is the... Okay, so I believe that that transistor right there is our oscillator, and the top of it should be at 7.9 volts. Which side's the top of it? Lead that pin. So we're in voltage mode, we got those. Pick up the chassis ground. .9. Okay. -2.2. That's right. That's the... So that's because this is a JFET, so the gate itself is going to have a negative bias. And then that one there, 7.4. And that was... So what was I just probing the... Yeah, okay, so I was probing the wrong one. So 7.4, where it's supposed to be 7.9. So... we're in the realm of conceivable here. And our VCO control voltage right now is 2.6. Trying to figure out a good place to stick this multimeter probe so that I can like stop holding it maybe. 2.6. So what happens if we change the inductor slug along with this? Does it compensate? It does. Right, and so normally you really probably wouldn't want to do this because you're like kind of gorking the whole calibration thing, but so I'm changing the inductor in the VCO tank, and I see the voltage controlled oscillator control voltage compensating for it, right? And so it's like it's locked. So it's like the VCO is locked. It's like VCO is locked. Alright, we go back to the receive chain. Pinned out of the attenuator is the first mixer. First mixer is a passive double balance type consisting of T1, T2, and U1. High side injection at 13 dBm is delivered to the first mixer from the second RX buffer. Which makes me wonder, is it possible that like it's like is the LO working but the buffer is not? Doesn't make any sense. So we injected a signal past the LO mixer and it still didn't do anything. Which makes me think I should probably continue to focus on higher up the chain. So the receiver system. What does the receiver system depend on? So the receiver system needs 9.6 volts on 13, 14. 9.54, good enough. Needs 2.6 volts on pin 15. 2.593. It needs 1.9 volts on 16. 12, 13, 14, 15, 16. 1.889. It needs 0 volts on 17. 17? 0 volts. 0.2 volts on 18. 0.186. And 19 is our RF input, and that's like 0.84, which will be 0.87. 1.7 volts on pin 20. We've got 1.877. 3.7 volts on pin 21. 3.7 volts is even. 3.7 volts on pin 22. We got that. 2.6 on 23. 2.59. 3.1 volts on 24. 3.04. Wild. Okay. So we're not getting any squelch action, which begs the question, what is squelch action supposed to do? Pin 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Hello. Peekaboo. Right. Pin 11 has, according to service manual, 4.2 volts on no signal, 0 volts. Note 7. Note 7. Measured on the receive mode with on-channel unmodulated signal level of minus 20 dBm. Okay. So, if I feed this minus 20 dBm, this should drop. 144.39 megahertz. And that's a whole bunch of butt kiss. Nothing. Got that out through RF out. $19. Yep, still just no sign of life. Just nothing. 15. Alright, so I'm toggling on and off the RF generator, and I'm seeing absolutely no change or sign of life at all. Alright, which makes me really start to question my sanity as far as like 45.1 megahertz. So I'm just sitting here probing, like, can I find the IF? Well, dang. I've got no freaking idea. Megahertz. I guess we're in the realm of... Oh, okay. Well, I'm an idiot. Oh, man. Helps if you plug it in. Okay, so all of the testing we have done so far means nothing. Cool. RF generator amplitude, because we didn't have the receiver plugged in at all. So, on versus off receive signal is on pin 11. Dip doop. Yeah. So with no signal, we've got have signal there. RF analyzer, RF generator, amplitude off. No signal. 4.2 volts on pin 11. What have I done? Have a meter in AC mode, that's what. Well, that's what I've done. Okay, let's... Okay. 4.5 volts. No signal. Let's plug the receiver in. Watch that 4.5 volts. And now when we turn the signal on, still nothing. Still a whole lot of nothing. Okay. And now when I go to the analyzer, wide open mode on the antenna. Let's check to see if I'm on the antenna. I'm not. Hey, look at that. Okay. All right, so it helps if you actually have everything plugged in correctly. So what I've got is I'm injecting 144.39 megahertz here. It's going through the whole front end, it's going through the mixer, and then I've got a receiver set for 45.1 megahertz, which is your, conversion. Well, it's the IF, right? And so I can sit here and probe, and we can hear it. That's the 1 kilohertz we're injecting, and that we're now receiving at a completely, totally different frequency. How cool is that? Okay, so that's the first sign of sanity all night. That's pretty fantastic. And so now, if I was to try and probe in here around like pin 19, I'm receiving stuff all over the place. Like the whole, like just the fact that I'm close is, yeah, we're definitely got lots of signal. So I'm not even touching it. Like I'm just got a little antenna near the final amplifier. We're going to the receiver fine. We are going into the receiver absolutely fine. So it's like 2 and 3. Tell me more about this audio chain. Power amplifier, transmit, power control, voice path, receive, voice path. Receive. Alright, here we go. Receiver backend. Right, so the receiver backend is pretty much everything after the mixer. So Q51 amplifies the signal. Q51, the output of Q51 is filtered by the 4-pole crystal filter, which is this. We were then able to hear our IF signal out, like on the output of it here. The 45.1 megahertz first IF signal is applied to the second mixer section of U51. A 44.645 megahertz crystal oscillator provides the low side injection signal. Really? 44.645. You say. And I'm willing to bet that's probably the crystal right there. So where is that? Or I guess really what pins are it on? 44.645 comes in on pin 15. Who's 12, 13, 14, 15? Who's willing to bet that this doesn't work? Haha. Okay. So that's bad. So we're supposed to have, so 144 megahertz comes in, it gets filtered, it gets mixed to 104, it gets mixed down to 45.1 megahertz. The 45.1 megahertz then goes through this wildly tight filter that's made up of these quartz crystals, and then it's mixed with a 44.645 megahertz oscillator, which then converts it down to 455 kilohertz. But we don't have, I've got my receiver here, and I'm listening around for 44.645, and it's not in here. Like there is none of that going on. So I suspect that this crystal is probably dead. Cool. What do we got? far as random stuff laying around. Here's another random board. This is a UHF one, but it should be the same. Probably going to be the same IF section, right? 44.645 megahertz with a lot of shmoo around it. That is a bummer. Well, no time like the present. Let's see if we can get this crystal off of this random board I got laying around. Soldering iron, solder. I feel like I probably should try and get some of the shmoo out of here. Yeah, so this donor radio, let's see, what did it have? It had good RX, no display, no transmit power, no will to live. Okay, alright, yeah, that sounds like... So if the whole RX chain on this side worked, then we definitely know that all of this is fine. Unfortunately, since the UHF, like the whole board is different, we can't just swap in the whole board. And if I had a spare VHF board, I would be trying to fix that one too, because the VHF radios are much more useful to me than the UHF radios, because VHF is APRS and UHF is repeaters, and the unfortunate part about repeaters is that you need to talk to people, and statistically I don't really want to talk to hams. So the UHF ones don't do much good. I don't know. You can see how much success I have getting this crystal out of here. Now that we've got some shmoo released and strange. I think one of my friends has mentioned before that losing the second IF crystal like this is pretty common. So I probably shouldn't be overly surprised that this ends up being failure mode here. I'm looking for tweezers so that I don't stop burning myself and get more leverage. The not burning myself part is really exciting. Okay, so did the crystal actually survive that hack job? Signs are pointing to yes. More or less. Oh man. Okay. Ha ha! There's one 44.645 megahertz crystal. Only some damage in shipping and handling. Clean up the leads, and there it is. So that's the easy part. is butchering one off of a donor. Now we need to get this board out and replace it. So or presumptively good one. We'll put that in a nice special place so that I can lose it later. Two pieces of coax unplugged. Then T10 Torx. One board. So now we're trying to get the whole board out of the chassis. So that's 2 screws. Three screws. 4 screws. 5 screws. 6 screws. 7 screws. Rude. 1, 2, 3, 4, 5, 6, 7. Okay. So now all we've got holding in this is the connection tension on the 14-pin through the chassis feed through action. So we'll take our precision prying device here and kind of lift up on board. Lift up on board somewhere else, and out she comes. There you go. A common failure mode for these is that this contact here gets dirty. So I should get some sort of slight abrasive. And by slight abrasive, I mean like paper. I'm just going to wipe that off a little bit. Okay, so we got one VHF board out, and my suspicion is that crystal is unhappy. See, that one came out real nice and easy. So now I've got to clean up those holes. This part always sucks. See, that joke would have been funnier if I was able to actually find my solder sucker right now. Hello? 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 Ah, there we go. Solder sucker. One hole. Second hole. Okay, we'll kind of pull that shmoo out of there. One would hope that this shmoo isn't as important. So this sort of shmoo that's like holding stuff down, pretty important for land mobile radio in the generic sense, because who knows how much vibration, shock load it's going to be undergoing and experiencing. So, you know, it's kind of a reasonable thing. I'm less concerned about it. It's like I'm certainly not going to like bother trying to like put shmoo back in here to glue the stuff back down, because my intended application for this radio is sit somewhere and receive packet radio. And so I'm not too concerned about, like, I'm certainly not going to be trying to glue this stuff down, because I'm not expecting this thing to get shock loaded too much. There we go. Just trying to get these pins. Oh man. So of course, you know, the challenge is it doesn't want to go in. And I have to try and get it in at least enough that I can then solder it the rest of the way. If I get lucky. I did not. I did not get lucky. You only get to bend the pin so many times in life, and I just spent one. So I've got the whole pins lined up, so now I'm just going to try and melt our way into it. I'm certainly not going to get it cleaned up enough to be able to just like drop in cleanly. That's just not reasonable. Ho 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 ho, that's not pretty. Oh, I'd like some positive confirmation that that actually made it in. I don't think I'm going to get it. Okay, well, so I made a hack job of the soldering, but I'm highly interested to see what if we were to just plug this back in. If like we would immediately get sign of life that we were not getting before, right? And if that fixes it, then we're definitely gonna clean it up a little bit more. Okay. Power. So I haven't even attached the antenna yet, and you can already hear it. So yeah, that was our problem. 1 microvolt. There it is. Yeah, so everything in the receive chain was working totally fine until it got to the audio processor chip that took it from 45 megahertz down to 455 kilohertz for the final processing and the actual... and there's that APERS packet. Worked perfectly fine, except that this second local oscillator frequency, right, because the first local oscillator frequency is the variable one that is synthesized depending on what channel you're listening to, so it's going to be 45.1 plus whatever your receive frequency is. That one's over here, and that was working fine. It was this fixed, simple, just between 45 megahertz down to 455 kilohertz that was bad. So we install that. I'm going to need to solder it in nicer than that because it's just kind of like tacked on there essentially right now. But there's 1 microvolt. There's half a microvolt. There's 0.3 microvolts, and you can hear some hiss on it. There's 0.2 microvolts. There's 0.14, and so that's, at that point it's almost entirely noise. And 0.1 is entirely noise, so I think I want my squelch about there. And so we'll come back. Okay, so I set the squelch pot back to kind of what I want, because that was, we fiddled with that originally. So yeah, so, you know, man, if you made it through this, I hope you enjoyed it. But yeah, so it was dead IF, we've replaced that, everything else immediately came back to life. This, which was a deaf M120, is now no longer a deaf M120. So I'll solder that crystal better, button the whole thing back up, put a note fixed on it, and it'll get built into an APRS digipeater, and I'll probably deploy it somewhere. So thanks for watching. See you next time.